Okay, can you see the slides on the screen? Right, okay. So let's move on with dry etching. We've discussed wet etch before the break. And today we're going to finish off etching, okay? So let's move on to dry etch. So dry etch is the process, so alternative to wet etch, and it's carried out in plasma condition. In plasma condition, there's no wet chemical involved at all, okay? So it can be generally anisotropic. It can also be isotropic in certain cases. Anisotropic is unidirectional, where you have one etching direction that is dominant over other directions. Okay, so the basic mechanisms involve sputtering. So sputter, nanti tak akan belajar sputter dalam thin film deposition. So we're going to see later on why is this involved in etching process. Chemical etching, isotropic, energy-driven ion enhanced etching, inhibitor protected sidewall, ion enhanced etching, and it is going to involve plasma reactors, okay, plasma reactors of various kinds. So characteristic of plasma or dry etch, it is less selective. It is anisotropic etch is also possible, and mainly the case where when you use dry etch, okay, and there's no hazardous chemicals like TIMA, KOH, NOH, HF, like what we discussed before in the wet etch, but it poses some other risk or hazards due to the usage of plasma. Okay, it involves hazardous gases, it involves RF power in the case of RF etch, okay, radio frequency assisted etch. So there's power safety risk involved. So there are three main types of plasma etching. The first one is physical or sputter etch, where you remove using physical momentum, right? The second one is chemical etch, and then the third one is combination of both, combined physical and chemical etch. So what is plasma? We've discussed briefly before. Plasma is ionized gas. So in this case, we normally use argon as our plasma. So the argon here will be in the form of plasma or Ar plus. Okay, AR plus or argon ion. So the ionized argon gas, ionized argon gas. So plasma. So we supply argon as the incoming gas, and then we strip off the electron, and then the argon will turn into argon ions. Significantly increases the reactivity of gas molecules. So a typical plasma chamber looks like below. Okay, RF power input as the supply, and then you have your wafer and your film to be etched. Then kalau you ada something here, then you're going to have material X, for example, that you want to etch. And then you have plasma build up in between two electrodes. So these, say this one is positive electrodes, and this one is a negative electrode that is grounded. Okay, yang atas tu ada dia punya input power, input RF, bawah tu is grounded. Then you generate your plasma in between. So argon gas akan fill up the space in between, and then the gas will be turned into ions. Okay, and ion here will be the plasma. Then vacuum pump to vacuum the chamber. So did you work on any plasma system before during your FYP? Anyone working on plasma system? Ada? Right, anyone working on vacuum pump related systems for your FYP? Yang kena ada vacuum? Ada. So before you generate the plasma, you have to evacuate this. The whole thing here is the chamber. This whole thing here is the chamber. So briefly, bila you run this system, you need to insert your sample. Sample ni wafer ni dengan your film to be able to insert your sample into the chamber, you have to vent the chamber. Vent means you kena purge nitrogen masuk dalam chamber. Nitrogen untuk fill the nitrogen into the chamber so that the pressure in the chamber matches atmospheric pressure. Kalau boleh buka. Kalau dalam tu dia vacuum, tapi kita punya luar ni atmospheric pressure, then obviously you can open because it's sucking. Okay, dia dalam vacuum, luar atmospheric. So the pressure difference leads to the sample cannot be removed because you cannot open the door. To be able to do that, you have to vent the chamber. Vent, this is the term that we use in order to fill up the chamber with air or nitrogen. Vent, VNT. So then we vent nitrogen, samakan, make sure the pressure of the chamber is equal to the atmospheric pressure. So there's no pressure difference, then only you can open. Bila you start the process, before you generate the plasma, you have to evacuate the chamber again. You masuk sample, tutup pintu. Then the current pressure in the chamber is still equal to the atmospheric pressure. So then plasma cannot be generated because too much of air inside. So what you have to do is you have to evacuate the chamber. Evacuate tu maksudnya create vacuum lah. Create vacuum by using this vacuum pump. Right, so typically we pump the chamber, we suck the air, pump the chamber down to around 10 minus 6, for example, or at least 10 minus 5 lah, 10 minus 5 at least. 10 minus 6 is obviously better. Then only you inject the argon and then supply the input power in order to generate plasma. Kalau you nak generate plasma dalam keadaan atmospheric pressure, it's possible, but then it's very, very difficult. You have to evacuate the chamber first. So at 10 minus 5 or 10 minus 6 torr, then the argon gas comes in, and you supply the input, and then plasma will be generated. And that is the point where you get to see the plasma in different colors. Purple or, different color depending on the gas that you use to generate plasma. Okay. Pernah tengok plasma tak dalam lab sebelum ni? Anyone has seen plasma on sputtering system maybe? Pernah tengok tak plasma with your naked eyes? Anyone? Tak pernah tengok plasma? The final year ni tak pernah tengok ya? Nanti saya bagi video lah. So kalau you get to run sputtering process, if anyone has done sputtering before, then you could have seen or may have seen the plasma in the chamber. So plasma ni kita guna untuk etching, right? Plasma untuk etching. Plasma ni kita boleh manipulate for some other processes as well. Tapi in this context, we're talking about etching. Okay, nanti kita akan discuss in thin film deposition. We can also use plasma to deposit films, silicon nitride, oxide, metals, carbide, many other materials. Right? Kita boleh guna plasma juga. Right? So physical sputter etch, very directional and isotropic in nature because it's one direction dominates others. Very poor selectivity, usually 1:1. Ions accelerated by electric field bombard the wafer surface. So ion yang kita guna dalam plasma is accelerated by electric field. Electric field akan accelerate, akan bagi energy kat dia, and it will just bombard the wafer surface. Dia akan langgar macam dia, the physical effect is like dia tumbuk lah, tumbuk dia remove macam dia dented lah, dent the surface if you like. So the exact reverse process of sputter deposition here, wafer is target. So this exact the opposite of this process is called deposition. Okay, deposition kita akan belajar selepas diffusion, then deposition. Etching is removal, remember? Kita remove. Deposition is what you want to add. You deposit a new layer. So that's why I mentioned this now. We use the same plasma to do either process, either etching or deposition, depending on the details of the process. Okay? So kita akan belajar the very same plasma untuk deposition juga elektron. Jadi saya akan tunjuk. So ion in this case is for milling Milling to means you not clear the area of flow for clearing of contact before metal depth. So in this case, the ions say accelerated to the surface and to remove this area from say resist. Okay, so that's one. So the second one is called chemical etch. The first one was physical etch. The second one is chemical etch, which is a non-directional or isotropic. The first one was anisotropic, physical and iso. And chemical is isotropic, so that means the etching rate is equal in all directions, just like what we discussed during wet etching. So very high selectivity. You can see the removal here. Nampak kan dia remove rounded punya area macam kita discuss waktu wet etch hari tu. So it attacks all angles with pretty much similar etch rates. Plasma creates highly reactive species called free radicals. Radicals are not charged, so there's no directionality. Okay, so the key here in this chemical etch dry etching, kita pakai radical. And radical there's no charge, so there's no directionality because you cannot accelerate the radicals into one specific direction. The way you accelerated ions using electric field in the physical etch. So that's why physical etch is anisotropic, chemical etch is isotropic. Useful for blanket firm removal, for example, etching of resist. Okay, remember last time we talked about etching, we talked about removing the resist when we talk about the rework process. And kita discuss tentang rework, you know, remove resist in all directions. So you have to do it blanket. Okay, dalam manufacturing kita pakai term blanket. Apa maksud blanket? What is blanket? What do you understand by blanket? Bukan selimut lah, dalam konteks discourse. What is blanket? Anyone? Term ni banyak pakai dalam fab. What is blanket? Dia sebut blanket means what? Juaria set lapisan. Okay, others? Dia cakap blanket apa maksudnya? Nanti you pergi intern nanti dia akan pakai keyword ni, blanket. Lagi? Ada lagi? Selain juaria. Balutan luar. Okay, Hadi balutan luar. Right, any other? Useful for blanket film removal. Layering, okay, right? Okay, layering. So, lebih kurang layering balutan luar. Lapisan, you punya impression is same. So let me see and if you have any other impression of the definition. Blanket, apa maksud blanket? Coating, okay, pretty much like lapisan. So maknanya you punya impression sekarang on the word blanket tu sama, lebih kurang. Any other different impression of the word blanket? You pergi, I think at least wafer fab lah. Other industry pun would probably use the same word, I think, but I'm not sure, of course. Any other? Tak ada. Bila kita sebut blanket in manufacturing, it means all. Bukan coating, bukan layer, bukan balutan. Well, the literal definition is like selimut kan, satu layer. Blanket means all. Maksudnya you tak remove certain areas, but you keep certain areas. Blanket means all. So dia akan cakap, do we have to do this blanket on all lots, on all wafers? Blanket means semua. Maksudnya in this case, if you want to etch, not etch, etching the resist, well, technically is under chemical etch. Kalau dia cakap blanket firm removal means kita nak remove semua resist tu. Maknanya isotropic etching is okay, it's fine. Because you don't want to keep certain areas of the resist for the rework. Instead, you want to remove all. You want to remove blanket. Okay, the same goes to when you do deposition later on. So dalam fab mana cakap, so do we deposit blanket? Deposit blanket means deposit semua. Dia bukan you deposit certain areas on the wafers, but you mask certain areas, for example. So that's what it means by blanket. So kerap pakai dalam manufacturing. So just nanti tengok kalau pergi internship dekat wafer fab especially, you will listen to this, you will hear this many times. So blanket here means all. Sebab kita nak remove resist kan, you have done the mist process of CED during the etching, during the lithography. So remember, bila you buat lithography, you mist process, you did something wrong, you still can remove the resist by rework process, and this is done by etching. Etching yang pakai isotropic chemical etching. Okay, it's not like one directional kind of etching, but it's just blanket removal. Okay, so that's why kita guna untuk etching process, because you want to remove all anyway, right? So clear blanket. Next, a physical and chemical etching. So combines directionality with good selectivity used for patterning of submicron features through resist. It can be done on contacts, via polysilicon metal. Ni semua layer yang kita akan belajar nanti ya. Contacts, so bila you print hole ni, kita panggil dia contact holes. VR pun sama juga, but then it depends on the, sorry, contact ni it means the metal contact. VR ni is the hole hole ni kita panggil VR, dalam fab kita panggil dia VR. So actually it means hole. VRD means you want to connect one metal to another through a VR, through a hole. Okay, nanti kita akan tengok the interconnect bila we finish off all the processes. Right, polysilicon is the gate, the layer that where you print the gate for your MOSFET, for example, the gate ox, the source drain. So this is the polysilicon, and the metal for your contact. Okay, so you can combine your physical and chemical etching in order to deliver certain quality of the layers. So for example, if you talk about a highly selective silicon etch, ini RIE, RIE is under, the RIE is under physical sputter etch, high directionality, highly anisotropic. You can see here, RIE means reactive ion etch. Reactive. So this is one machine or one process that we have under dry etching. Reactive ion etching, RIE. RIE. Highly selective and anisotropic process. You can etch silicon here. For example, you can see the schematic here. Say you have silicon. You have silicon here, and then you have gate ox very thin there, and then you have polysilicon here. And you think kat sini is very highly directional. Maknanya we keep those features with high aspect ratio. Maknanya dia punya height is very high, the width is very small, and we learned about aspect ratio before. Height over width, right? Aspect ratio, and we will remove these portions using RIE, kita etch, and it's a very highly directional process. Kita remove one direction. So in this case, kalau you pakai etching, habis, all gone, but dia isotropic. In this case, you have to use anisotropic, so which is RIE process. Okay, so this is one example. So deep RIE, so another RIE, another type of RIE is called DRIE. Ni pun under RIE juga, but then it's deep. Okay, how deep? Look at how deep there. You tengok height of Bosch tu, dia punya depth dia, berapa deep? How deep is the Bosch punya depth? Dia macam engrave lah, you engrave, but then you use deep RIE process, DRIE. What is the depth of the Bosch punya features tu? Can you estimate from the scale bar? Berapa tu dia punya depth? Anyone? You can write down. Look at the scale bar there, the given scale bar in the picture, and then look at the depth of the Bosch punya features. Anyone? How deep is that? How deep? Look at the scale bar there. Scale bar is given already, right? 180 micron. Not quite. It's lesser. You tengok ni scale bar ni. Scale bar is 90 micron, right? So you can look at this. Oh, scale bar ni mai sini. Yeah, pretty much, Mimi. 90, yeah, of course, dia ada angle lah kan, so it won't be accurate exactly. Yeah, that's probably about 100 micron or so. If you put this scale bar on this depth, that's probably slightly over 90. So maybe 100, 110, 120, somewhere there. Sebab the angle is a bit hard to estimate, but roughly there. Okay, so the depth is like 100 of microns, okay, 100 of microns, which is very, very deep. If you compare to these features, for example, kita feature ni is like scale bar is 200 nanometer, and your depth here is perhaps 200 plus nanometer, which is highly anisotropic, but then it's not deep enough. If you compare that 200 plus nanometer versus this 100 micron, okay, so 1000 times deeper, okay, lagi dalam. So that's why we call it deep RIE. So you etch like hundreds of microns anisotropically. So that's why we call it deep RIE. Okay, so yeah, it can be done as well, deep RIE. But if you talk about features like MOSFET, high-speed transistors, we don't go that deep. Okay, we typically go down to hundreds of nanometers max. Okay, ini memang special case lah. Kalau nak print say USM, you can just do litho of USM. You boleh buat mask USM atau physics USM, and then you etch area-area yang selain physics USM tu macam Bosch ni. You etch deep enough, then you eventually have your physics USM engraving, if you like, right? Tapi pakai litho and etch lah, right? So you can do that by using fabrication processes. So ion-assisted etching and sidewall preservation, improved directionality of RIE, is vertical sidewall. You can see here, ions are directional, but then you protect the sidewall. Okay, you protect the sidewall. So therefore, no ion bombardment on the walls. Okay, polymers are deposited during the etch process, protect sidewall from the chemical attack. So it can be done as well. Right, typical gases for plasma etch. We typically use argon, okay, for an isotropic process. Okay, argon. Then aniso. So for resist removal, etching, remember, etching is iso because you want to remove blanket. You want to remove all. Okay. Kalau tadi aniso kita nak korek kat certain area je kan, kita nak etch certain area. But this one is like blanket removal. Aluminium and other metals, you need to use BCl3, Cl2, CCl4 if you want to etch aluminium and other metals. Okay. So kalau ini etch silicon dioxide, nitride, single crystal silicon, polysilicon, you can use CF4, HBr, SF6. Okay, macam tadi tu, you can use SF6 untuk remove silicon. Tungsten, if you want to etch tungsten from the wafer, from the films, you need to use NF3 as your gas. Okay, so that means to be able to do different etching of different material, you need to use different gas in the process. Okay, process control in plasma etch. There are a few process parameters that you have to use. For example, RF power, gas flow, chamber pressure, temperature, electrode gap, okay, many other. You can just come to this schematic tadi. Yeah. So there are so many different parameters that you can vary in order to vary the process. Gas inlet, vacuum level, electrode separation distance, RF power input, chamber size, chamber geometry, so many things, right? So many things. The application, etching, removal of silicon, removal of films from substrate, or removal of substrate material itself. So you can remove silicon nitride on silicon, you can remove silicon dioxide on silicon, you can remove resist on silicon, you can also remove silicon, part of silicon from the silicon wafer itself, right? So etching is needed for analytical purposes. You boleh etch certain features in order for you to send the sample for SEM to view certain angle, for example. Sebab kalau kita etch, you won't be able to see the design angle, for example. Ataupun you nak buat pattern transfer lah, because you need to do the etching in order to enable pattern transfer, just like when we pattern our silicon dioxide, for example. Okay, ni sama aja. Removal of materials, analytical purpose. So kalau you nak study certain tests, or you want to open certain holes so that you can probe at certain specific areas for you to understand defects ke, you nak potong kalau ada defect, let's say macam ni kan, ni wafer silicon, then you have some defects that you don't know what is the material, for example, then you can actually cut, you can etch the wafer, sorry, the defects. You boleh potong di half ke, for example, so that you can see another half. Say remove this portion and then you send for SEM to view from certain angles. And you can do EDX, for example, electron dispersive X-ray, untuk tengok apa dia punya elemen dalam tu, so that you know the origin of the defects. Ataupun you troubleshoot, tak tahu dia main dari mana, you have to do EDX, then only you see carbon ke, silicon ke, tungsten ke, then you can slowly relate to which particular process that could have caused the formation of the defects. Okay, kalau tidak, you just don't know, because you can just see defect, but then you have no idea of what is the source of the defects. Pattern transfer untuk lithography, okay, kita dah discuss. So wafer cleaning is also another form of etching. Okay, hari tu kita discuss kan on the RCA, Radio Corporation of America, right? A patented process by Radio Corporation of America, but it's actually a cleaning process. So to be able to do a cleaning process, you have to remove the defects, right? You have to remove the oxide, you have to remove impurities, you have to remove organic residues, and to be able to remove all this stuff, you have to do the etching process. Okay, etching to remove oxide, etching to remove organic materials, etching to remove metals, for example. So cleaning pun essentially is etching process. It's a form of etching process, but then we call it cleaning. Cumanya the very process that goes on in the bath is actually etching. Okay. So contamination sources, we discussed this one briefly during the clean room process. So contamination can come from range of different sources, like the wafer holder itself, the wafer box, wafer handling, the Teflon particle from process chambers, from robot arm, from friction of robot arm with the materials in the equipment, for example, residual of the resist, slurry for the cleaning, for the CMP. The slurry itself can cause scratches, can cause defects, corrosion of metals, right? Solvent stains, polymer deposition, airborne particles. Hari itu kita discuss waktu kita discuss clean room class berapa tu, right? Contamination in the gases and the chemicals, right? ESD, electrostatic discharge, and operator induced, smoker or hair, or skin or clothing or makeup or anything, right? So that's why that's the whole idea of wearing your PPE, personal protective equipment, so that you are protecting the wafers against you, okay, instead of protecting you from the wafers, right? Okay, so we're protecting the devices, the products against us, because we are the one who cause contamination, right? So wafer cleaning option, RCA, we discussed, right? Okay, to remove organic materials, organic contamination, metal contamination, oxide. So essentially the cleaning process is also an etching process. So how to do the RCA? So there are three steps, RCA 1, and then the first step is called RCA 1, where you use this volume of chemical, this volume ratio, 5 volume of DI water, 1 part of hydrogen peroxide, and 1 part of ammonium hydroxide, okay, to remove organic residues, also remove light metals. Okay, so we call that as RCA1. So the second step is called BOE, buffered oxide etch. Kita guna etcher je untuk remove oxide, 100 to 1. So you use 100 parts of DI water and 1 part of HF. Bukan terbalik, kita nak tak terlalu concentrated. Kita nak ada diluted. To remove any native oxide grown in step 1. So remember we talked about native oxide before this. And then the last step is called RCA2. Okay, RCA1 for organic, then oxide removal by HF, and then RCA2, 6 part of DI water, 1 part of hydrogen peroxide, and then 1 part of HCl, hydrochloric acid, to remove heavy metals. So the moment you finish your RCA process, your wafers should be free from organic materials, organic contaminants, native oxide, and also heavy metals. Then the wafers are ready for the next process. Okay. So wet photoresist strip is also available. Can use this by etching. It's called piranha etch. Piranha etch. Kalau dalam fact itu panggil piranha etch. Combining sulfuric and hydrogen peroxide. Sulfuric acid H2SO4 plus H2O2. Sulfuric plus hydrogen peroxide. Okay, and then solvent strippers such as PRS 3000. So we call that process as piranha etch. So it's a wet resist strip process. So this is how it looks like. The wet etch process in an immersion tank. Dia macam sinki lah, sinki besar, but we call that bath or tank. So kita dip all the wafers. If you talk about wet etch, we dip all the wafers in batches. Masuk sekali rendam for like say 30 seconds at certain temperature so that you can remove certain things, right? So it depends on what are you trying to remove in that particular process. So in summary, for etching, we're done with etching. So there are a few things that you have to understand. So it is a form of pattern transfer process. And by this time, we know that to be able to have your pattern transferred from the reticle, from the mask, you cannot only rely on lithography, but you also have to remove the unwanted materials by etching. So pattern transfer involves lithography and etching because eventually you want to remove the resist, right? So resist is not supposed to be there. It's just a medium for you to do the pattern transfer, but it's not supposed to be there because it is a polymeric compound. Kalau you lupa etching, then just imagine you will cross-contaminate your next processing chamber with polymers. Polymer yang ada dalam etching lah, yang ada dalam resist lah, because you don't remove the resist. So dia akan jadi cross-contamination, chamber will be shut down, process will be shut down, and then major problem. Right, two critical issues. Selectivity, we discussed this one. Okay, selectivity, S, R1 over R2. Directionality, we discussed as well. When you discuss about this, then equally on aspect ratio. And then we discussed about wet etching, isotropic, like HF, for example. And we've also discussed about an isotropic process like KOH, NOH, or TIMA that will produce some kind of pyramids on the surface due to the difference in etch rate of 100 plane versus 101 plane. And then we've also discussed today on dry etching, which can be physical, which is anisotropic. It can also be chemical, which is isotropic, like etching process, and you can also combine both to end up with certain features. Right? So we're done with etching. I want you to go back and try to think of this question before I finish. You have a lithography system that can only print features with minimum CD of 200. You are the system, lithography CD can only print down to 200 nanometer, but you need to combine this capability, 200, with an etching process in order to print CD of 100 nanometer. Okay, sekarang kalau you guna litho je boleh print down to 200 saja, but you need to print 100. You need to stretch the capability of your litho etch processes. So I want you to think of what is your proposed process in order to get a 100 nanometer of your resist CD. And CD of your resist, ni resist, PR photoresist. You want to get 100 nanometer of your CD, but your system is capable of 200 only. Tapi you nak halfkan capability. How do you do that? Okay, kita akan discuss this question tomorrow during the class. Okay, then we move on to diffusion. Right? So any questions so far on etching? Ada soalan? Soalan ni is another form of stretching your fundamental. You belajar capable 200, but then you need to stretch to 100. How? Soalan? Let's move, okay? Is it okay so far? Understand? Do you understand the content of etching? Okay, let me see this question. Coba ya. Must use the same system and just to find the limit to 100 even system? Yeah. Your system is capable of 200 minimum. You tak boleh print 150, you cannot print 120, you can go, of course, 100 memang tak boleh lah. But then, you punya process intend to produce 100. Your system boleh pergi 200 je minimum. Kita dah belajarkan the limit of the lithography system. Kalau 200 means resolution 200, with good resolution at 200 only. You cannot stretch down to 100 in this case. But then with certain helps, certain tricks, certain techniques from etching process, you can actually combine litho plus etch to deliver 100 nanometer successfully. How? So we're going to discuss the how tomorrow. So I want you to come up with your suggestions, proposals, and then maybe kita boleh draw dekat whiteboard ke esok, and you might want to share your whiteboard as well, or some sketch, and we see how it goes. How do you produce 100 nanometer using combination of 200 nanometer litho plus etch process? Okay, clear soalan tu? 2 plus already. So I assume no question then. So I'll see you tomorrow. Bye bye. Take care. Assalamualaikum.